The next talk, Shiliang from University of Illinois Urbana-Champaign will be talking about Newell-Littlewood numbers. And if you have any questions in the middle, please put it in chat or feel free to unmute yourself and ask.
Well, thank you for having me. So today I'm going to talk about Newell-Littlewood numbers. This is based on joint work with Gideon Relowitz, Nicolas Rassier, and Alexander Young. So let me start with something very more classical topic, Littlewood Richardson coefficient. So for a n-dimensional complex vector space V and a partition lambda of at most n parts, the Well module as lambda is an irreducible representation of a general linear group. So these Littlewood Richardson coefficients, C lambda mu nu, is then the tensor product multiplicity of these Well modules. So you take the tensor product and you decompose it. The coefficient would be given by this Littlewood Richardson coefficient. Just to keep it short, I also refer to it as LR coefficient. So these LR coefficients also appears in other settings, including things in geometry, where these LR coefficients are the structure constant of the cohomology ring of Grassmannian. So if you take the cut product of two Schubert classes and you decompose, the coefficient would be given by these LR coefficients. And a more geometric interpretation would be if you take is that these are the intersection number of three Schubert varieties also inside the Grassmannian. In terms of representation theory of the symmetric group, these are the multiplicity of the spec module as lambda in the induced representation of S nu tensor S mu. So in other words, if you consider the character ring of symmetric group, these LR coefficients are also the structure constant of the ring. In terms of combinatorics, there are many combinatorial models that describes this Littlewood Richardson coefficients. Like it could be the number of Littlewood Richardson tableau, number of integral hives, number of puzzles, etc., etc. So now the main character of today's talk, the Newell-Littlewood numbers. These are defined in terms of these Littlewood Richardson coefficients. So for three partitions of at most n parts, the Newell-Littlewood number is the sum of product of three LR coefficients. These are the tensor product multiplicities of irreducible G modules in stable range, where G is Lie group of type B and C and or Dn. So that would be SO2n plus 1, SP2n, and SO2n. And by in stable range, I meant the length of nu, or the number of non-zero parts of nu, plus length of mu is less than or equals to n. So here I'm lying just a little bit, in the sense that in type D, if lambda n is non-zero, then S lambda is not irreducible. It's actually the direct sum of two irreducible ones, but that's will not be focusing on that in particular. So as with any of this tensor product multiplicities, one natural question to ask is, when's the Newell-Littlewood number non-zero? Now I'll try to answer the question in some sense, or to some extent. But first, I'll just take a detour and talk about eigenvalues of Hermitian matrices. For let A be an n by n Hermitian matrix, the spectrum of A is defined to be this lambda, where lambda i's are eigenvalues of A in weakly decreasing order. Now, famous Hermitian eigenvalue problem asks, so what mu nu lambda can be the spectra of Hermitian matrices A, B, and C with the property that A plus B equals C. Now, many necessary conditions on these spectra are given. This include work by Well in 1912, Fan in 1949, Litsky 1950, Weyland in 1955. And in 1962, Alfred Horn proposed a family of linear inequalities. And by linear, I meant linear in each of these lambda i's, mu i's, and nu i's. He proposed a family of linear inequalities that characterized spectra of these spectra of ABC. So these mu nu lambdas. Now the Hermitian eigenvalue problem is solved by Alexander Kryachko in 1998, where mu nu lambdas are the spectra of ABC with A plus B equals C, if and only if, first of all, the size of lambda equals size of mu plus size of mu, and this mu nu lambda satisfy what we call Horn inequalities. Now this solution posed by Kryachko, like these inequalities, are just slightly different from the ones proposed by Alfred Horn back in 1962. But it was later combining the work done by Knudsen and Tao. We can show that these are the exact same family of inequalities. Now, so how does that related to Littlewood-Richardson coefficients or Newell-Littlewood coefficient? Well, it turns out that in that same paper, Kryachko showed that for these three partitions, lambda mu nu, with the property that size of lambda equals size of mu plus size of mu, these stretched LR coefficients, C m lambda, m mu, and by stretch, I just mean like for m lambda, it's just m lambda 1, m lambda 2. You multiply m to each part of the partition. So if this is non-zero for some positive integer m, this if and only if lambda mu nu satisfy these Horn inequalities, like all of these. Okay, and now in 1999, Knudsen and Tao using these combinatorial model they developed called honeycombs. They proved that the LR coefficient C lambda mu nu is greater than 0 if and only if there exists some positive integer m such that the stretch LR coefficient is not 0. This is also later reproved by Anders Book and Dirksen Weyman in 2000. Now, as a corollary or combining their work with the work of Kryachko, we obtain a complete characterization of non-zero Littlewood-Richardson coefficients. So C lambda mu nu is greater than 0 if and only if, first of all, the size, we have the size constraint, and that lambda mu nu satisfy these Horn inequalities. Okay, now back to our Newell-Littlewood numbers. So recall the definition of Newell-Littlewood numbers. We have this sum of product of Littlewood-Richardson coefficients. Now, a simple observation is that if we assume the size of lambda equals size of mu plus size of mu, then these two numbers coincide. The reason is quite simple. So if we have the size condition and we know that alpha has to be contained in mu and gamma has to be contained in mu in order for this product to be non-zero, then we must have beta equals the empty partition and alpha equals nu, gamma equals mu. So so under the size constraint, we know the two numbers coincide. Now, this sort of building from this, we were able to show that this is work last year with Gidon Relowitz and Alex Young. So if the Newell-Littlewood number and nu mu lambda is non-zero, then this lambda mu nu satisfy any of the S3 permutation of Horn inequalities. What do I mean by S3 permutation? So for n equals 2, I'll just show you by example. For n equals 2, the Horn inequalities are exactly these three. So lambda 1 less than or equals to mu1 plus nu1, lambda 2 less than or equals to mu1 plus nu2, and mu2 plus nu1. And by S3 permutation, I just meant you can permute these lambda mu nus, and you can obtain these 6 inequalities. So for example, for this first one, we can permute well in any ways lambda mu nu, so we get mu1 less than or equals to lambda 1 plus nu1, and nu1 less than or equals to lambda 1 plus mu1. Yeah, so so these S3 permutations of Horn inequalities are a necessary condition for the Newell-Littlewood number to be non-zero. Now, there's more to that. We were able to extend these Horn inequalities, and we came up with this family, what we call extended Horn inequalities. And we were able to show that if the Newell-Littlewood number and nu mu lambda is non-zero, then these three partitions satisfy all these extended Horn inequalities. Another way to phrase that is that these extended Horn inequalities are all necessary for the Newell-Littlewood number to be non-vanishing. Right, and in fact, so what about the other direction? What about the sufficient part? So we showed that if the lengths of mu, nu, and lambda are all at most 2, and that the size of lambda plus size of mu plus size of nu is congruent to is an even number, and this condition is actually a sort of a trivial condition in the sense that if it is odd, then like the Newell-Littlewood number is trivially 0. So if the number of parts of these three partitions are all at most 2, then these extended Horn inequalities are also sufficient. And moreover, our most recent work, this is a work in preparation, we were able to show that if we have this size being even condition, which is sort of trivial, then lambda mu nu satisfying extended Horn inequalities. This is if and only if, since we already showed the necessary direction, if and only if there exists some positive integer m such that an m mu, m nu, and m lambda is non-zero. So this means that we obtain a description of this saturation cone of the Newell-Littlewood number. And that's it. Thank you.
Let's thank the speaker. Does anybody have a question? Well, so I have a question. Like these two theorems in this slide are based on those lengths adding up to an even number. Have you guys done anything with odd number then?
You mean like the size?
Yeah.
Oh, if it's odd, then it's trivially 0. The reason is that if you look at this definition, the sum of sides of mu, nu, and lambda equals 2 times the sum of sides of alpha, beta, and gamma. In order for anything to be non-zero.
Thanks.
Yeah, and this condition also corresponds to lambda plus mu plus nu being in the root lattice in type B and type C. Yeah.
I have a question.
Yeah.
So in the second theorem, you said there exists m. Do you have like a prediction on what m is?
That's a very good question. So I think it was in 2012, Stephen Sam proved that, so if you take the actual tensor product multiplicity, not just necessarily in the stable range, which is given by these Newell-Littlewood numbers. If you're taking if you take any tensor product multiplicity in type B, C, and D, so there exists M greater than 0 such that the tensor product multiplicity is non-zero if and only if if and only if the tensor product multiplicity of 2 mu, 2 nu, and 2 lambda is non-zero. This is Steve and Sam back in 2012. I think the name of that paper is something about symmetric quivers, invariant series, something.
Okay, thanks. But their condition is different from yours, right?
Well, what do you mean condition?
Like, for you, you said for them, they say it's 2, m equals 2, then it's non-zero.
Yeah. Well, it's.
Do you plug in 2?
Oh, no, I think so. His result was that if there exists any positive integer, then you can show that if you plug in 2, it's also non-zero.
Oh, okay. So if you can find 1, then 2 will be one of it.
Yeah.
Oh, okay. So in your case, basically you're saying like it also apply when you plug in 2. Oh, okay.
Yeah, and if you're able to show instead of 2, you can just have 1. That's the saturation problem, which is like for tensor product multiplicities, that's wrong in type B and type C, but conjecturally true in type D.
So which type are you working in, or it's general?
This is it doesn't matter if it's type B, type C, or type D here, but we're assuming that it's in the stable range. So we're assuming this condition. In their work, this is not a assumption.
Okay, I see.
Yeah.
Okay, thanks.
Yeah.
Any other questions? Okay, let's thank the speaker again.